Hello everyone, welcome to the lecture of data structures. In this lecture, you will come to know about one of the commonly used balanced binary search tree, the red-black tree. Okay, so let us look at that now. Uh, First, let us shortly review the binary search tree. Binary search tree or BST. We know that it is a good data structure for searching algorithms. Note that, or you can look at here, the BST is not only used for searching, but also it supports or used for finding predecessor, finding successor, finding minimum, finding maximum. In addition, it supports insertion of items or elements or nodes, and it also supports deletion of elements or nodes. Okay, uh, this is the a short summary of typical binary search tree. Okay, now let us focus on the balanced binary search tree, the red-black tree. That is our context. First, it is about the motivation of using the red-black tree. Okay, so let us look at the motivation of using red-black tree. Motivation. Uh, you can look at first. You can look at the performance of the not of the performance uh, of a binary search tree, and we know that the performance of binary search tree is you can look at here. Binary search tree is related to its height. Okay, so the performance of a binary search tree is related to its height, and we know that it is OAs. Okay, it is OAs. I think we all know about it. You and I, we all know about it. The issue is that in the worst case, you can look at here. In the worst case, this one, it could be ON, order of n, ON, where n is the number of items or nodes. Okay, that you can consider nodes or items. On the other hand, if you look at in this side, this is the best case. Okay? In the best case, it could be order of log n. Okay. Since in the best case, the height is order of log n. Thereafter, our goal is to get such a binary search tree in which the height would be this. Height would be this, O log n. Okay, O log n. So how? Yeah. Well, okay. So we want a balanced binary tree in which the height of the tree would be 4 log n. So how to get that? Note that we can achieve that by one of the balanced binary search tree by the red-black tree. Okay. And this lecture is on red-black tree. Okay. So we have come to know that the red-black tree is a balanced binary search tree, and it can ensure us height, ensure us the height of order of log n. Now we need to know what are the applications of it. Then we can use the red-black tree. Okay, so let us look at the application of it. You can see that most of the self-balancing binary search tree library functions like map and set in C++, tree set and tree map in Java use red-black tree. In addition, you can look at here, the red-black tree is used to implement CPU scheduling in Linux. Okay, CPU scheduling, and you can see that library functions we have in C++ and Java use red-black tree. And this is the short applications of red-black tree. And now let us look at the ins and outs of it. Okay. So first it is about the property. Every node is either red or black. The root and leaves are black. If a node is red, then both its parent and children are black. For each node X, all paths from the node to descendant leaves contain the same number of black nodes. I am directly reading from the slides, and sorry please. I know it is difficult to capture all the properties in one shot, right? So now let me explain this with the help of some examples. First, we can see how a red-black tree looks like. This is a red-black tree with height 4. This is a red-black tree with height 4. This. Now let me explain the properties. Every node is either red or black. Okay, you can see here this node is black. On the other hand, its child node 18, is red. Okay, but I know that you are mainly thinking about 3. Why it is black? And we know this nil, they are also black. These nils are also black. But why this is black? You will come to know about it very shortly. Let us move to the next property now. The property 2. The root and leaves are black. Okay, the root and leaves are black. You can see the root is black and the nil is black. Okay, that I told in the last slide also. So it means that the root and leaves cannot be red. Only the intermediate nodes can be read. You can see the intermediate node 18, 8 and 11 and 26, they are red. Okay, so now let us move on to the next slide. That is the property 3. Property 3. If a node is red, okay, we can consider this node, then both its parent parent is 7, and its children are black. These are the two. You can see here it is preserving the property. Okay. One more thing that I want to share with you. You can see that we can have consecutive black nodes, right? Yeah. consecutive black nodes. Okay, consecutive black nodes, but there should not be any consecutive red nodes. Okay, why it is like this, I told you that I'll explain in the next slide. Okay, I'll explain in the next slide. So let us, one point I want to tell you, uh, there should not be any consecutive red nodes, but there can have consecutive black nodes. Okay, so why consecutive black nodes? We will come to know in the next slide. So let us move on to the next slide, that is the property 4. Property 4. For each node x, all path from node to descendant leaves, okay, descendant leaves contain the same number of black nodes. Okay, so if you look at the node 7 in this one, node 7, it contains 2 black nodes for each path to descendant leaf nodes. Okay, if you look at the node 7, it contains 2 black nodes. Okay, 2 black nodes. We can move in this. 2. One is nil, another one is 3. Okay, now if you move in this way, throw 18, 10, 8 and nil, you can see in this way also, in this path also you have 2 black nodes. Okay, so for each node x, all path from the node to descendant leaves contain the same number of black nodes. So this is the property 4. Okay, so now I'm coming to the node 3. Node 3. If the node 3 is red, it will violate the property 4. Okay, it will violate the property 4. Okay, so for this node is black. Okay, one more thing that I want to share with you, mainly the number of black nodes. Okay, you saw that from 7 you have 2 black nodes to the descendant leaves. One more node we can look at. Suppose 22 or 20 or 10. It has at most, it has one, only nil. Okay, one nil. Okay, nil. Let me clear the screen. Yeah. So now, what I wanted to tell you that the number of black nodes in a path is called the black height. What I said, the number of black nodes in a path is called the black height. That means we are actually computing black height. Okay, this one, this, yeah, this. So this computing black height, and we are checking that whether it is mainly same or not. Okay, if it is same, then we can say that it is preserving the property 4. Okay, let me move on. Let me go to the next slide and talk a little bit in detail about the black height. You can look at here. Black height is mainly it is presented by the symbol BAs and of a node, suppose X. What this is, I am saying here, the black height of a node X. That means B is X. Okay. So what is black height? Especially, black height of a node is the number of black nodes on the path from X. That means from the node. Okay, from X. That means from the X to a leaf. To a leaf. I'm repeating, I know, but I have to make sure that you understand me. You are capturing, you are getting everything what I said. Okay, so note that. So again, black height of a node X is the number of black nodes. Is the number of black nodes on the path from X to leaf. Okay, note that note that it includes the leaf node. Okay, you can see to a leaf. So note that it includes the leaf, the nil leaf, but exclude. You can see exclude or not counting x itself. That means it is not counting the node itself. Okay, that is the point. So you can look at the nodes 20, 18 or 17. The 20 suppose. So if it is 20, you can see the black height is 2. So how black height you can move in this way? 18, 17. So one, another one is the nil. Okay, so 2. So in this way you can do the uh, computation for black height. Some other useful information that we have while computing the black height that we need to know. You can look at here. You can look at here for all nil leaves, black height is 0. Yeah, it's true because it should not include itself, right? And for root x, you can see the black height is equal to the black height of the tree. Yeah, that means if you want to compute the or want to know the black height of the tree, you can compute the black height of the root. Then you will get it. Okay. So we have come to know about the fundamental things. Now we can look at the operations that the red black tree supports. Okay. You can see that it supports all the operations supported by the typical binary search tree. One thing that you can see that C means we already know about this. All the operations run in O log n times with n nodes or with n items. Okay, that we already know for this. We are not for this. We are talking about in the motivation section, right? But some things that we need to know, especially in red black tree. In a red black tree, we encounter some issues while performing insertion and deletion. Okay, so while we perform insertion or deletion, we encounter some issues. What are the issues? The issues are like this. It may violate the properties of red black tree. Okay, so when we will perform the insertion and deletion, it may violate the properties of red black tree. So in the context, our goal is to maintain the property. Okay, so our goal is to maintain the property. But how? But how? Okay, let us look at that now. How to maintain the property? You can look at here by changing color or by recoloring. Same thing, changing the color or recoloring, or by rotation. Okay, so we can maintain the property by changing the color or by rotation. Okay, so let us look at these two. Changing color like this or recoloring. You have initially the color is like this. So you are changing the black to red and red to black. So this is very simple. Now it is about rotation. So you have a tree like this. So if the insertion violates the property of the red black tree, in that case you can do the right rotation or you can do the left rotation. It depends on the scenario. Okay, that we will come to know later. But one point that may arise in our mind, one question, I should not say one point, the question that may arise in our mind like this: does rotation preserve the key ordering? Okay, does the rotation preserve the key ordering? Uh, what I want to say, first we can look at how rotation is carried out or how rotation works. then we can look at this question. Later we can look at this question. So we can look at how to do the rotation. So rotation, right, rotate. So we are doing the right rotation. Okay. So we have this tree. We have this tree and we are performing right rotation of the Y node. Okay, parent node. You can do any node. I am doing the rotation for Y node. So if you rotate, then you can see that you will get like this. Okay, the Y will, and this is the second step after the rotation. Okay, this it will be like this. Okay. So now your X will become the parent of Y. Okay, so for this I have moved it up little because it will also be rotated, right? So moved it up. Now if you look at that, X, you can read X keeps his left side. It's true because no one is, because it is far behind Y. Okay? And Y keeps its right side. It is true because it is far behind X. Okay, but this one, the B, that is in between X and Y, very close. Okay, that is in between. Now you see they are very close. You can look at here. This one, the second, this one. So let me clear the screen. So this B, it is already marked. So this B, okay, this one, it is in between of X and Y. So what it is saying? It is saying that X's right child becomes Y's left child. Yeah, you can see. Yeah, I did that. That is the next one. Now you can look at here. X's and Y's parents change. Okay, and you get this after rotation. After right rotating of Y, you uh, get this tree. Okay, we will see it later when we will insert one item or one element or one node. Okay, that we will see. Now we can look at the left rotation. You can look at the left rotation here. So this is our tree. Okay, and we are trying to rotate X node. Okay, so when we do the rotation in the first step, it will become like this. It will become like this. So now as before, so these two, that means this side and this child of X and Y, there will be no interfere with them. Okay, that means no one will interrupt them. But this B as before, as in the right rotation. Now the B is the left child of Y. It will become the right child of B. Let me clear the screen. So now you can see here it has become the right side of X. You can read here. Y's left child becomes X's right side. And X's and Y's parents change. Okay, so it works in this way. So this is the way the left rotation and the right rotation works. We will have examples later when we will insert items in the tree. Okay, so let us look at how insertion is carried out. Okay. How insertion is carried out. So let us move on. Insertion. And what I want to share with you is that note that insertion is carried out by one node at a time. So you cannot add more than one node at a time. You can insert only one node at a time. Okay, that is the point. Moreover, uh, when we insert an item that we know already that it may violate the property of red black tree, right? So first thing that we can insert one node at a time, but this insertion may violate the property of the red black tree. Okay, this violation so it may violate the property of the red black tree that we already know, right? So uh, one more thing I want to tell you explicitly. It may violate the property. Property means we have the color, right? Color property, and also the black height property. This and also the these two I can tell you now, the color property and the black height property. So when we insert a node, it may violate the color property and also the black height property, right? So first I am talking about the color property. Okay, suppose we want to insert a node, then not then initially we need to decide. Okay, we need to decide what color to make the new node that we are inserting. So when we will insert a node, then it may violate the color property or may violate the black height property. We know we have 4 properties, but I am directly specifying 2 properties. Okay. So suppose first we are considering the the red color property. Okay. So when we want to mainly insert a new node, then first we need to decide the color of the new node. Okay, suppose the color of the new node is red. Okay, the color of the new node is red. The issue is that if the node is red, then it may violate property 2 and 3. Okay, how? It may violate property 2 and 3. How? We know that property 2 means the root and leaves are black. So if it is the first node, if it is a first node, and we know if it is a first node, that means it is a root, and root should be black. So it is violating property 2. Okay. One more thing, if a node is red, then its parent and both its children, I should say in this way, then both its parent and its children are black, but its parent may be red. So it may be the node. When you are adding or inserting a node, it may happens that its parent is red. So it may violate property 2 and 3 if we set the color of a new node red. Okay. So now we can see if we make it black. If we make it black. Okay. You can look at here now. If we set the color of a new node black, then you can see that it may violate property 4. How? We know that for each node x, all paths from the node to descendant leaves contain the same number of black nodes. So we are adding one more black node. So in that path, it will be the plus on path length or the black height number, right? So it will violate the property 4. Okay. So now what can I say? Mainly these are the mainly some issues, or these are the some issues that we will face while we will insert a new item. So first we need to decide the color, right? Red or black. Okay. So let us look at the basic idea of insertion, then we can decide the initial color. Okay. You can see the initial color here. You can look at here. When we insert a node Z, suppose the new node that we are inserting, it is Z. We set the color Z to red. That means initially we set that, or we mark it as a red color. We set the color of the new node to red. Okay. and we know that this may violate property 2 and 3. We know that. Okay. But the point is that, okay, you can look at here, P2 and P3 violation, that means property 2 and property 3 violations are easy to fix than property 4 violation. Okay, for this we are setting the color to red. Okay, so how to fix this issue or violations? We can recolor and rotate nodes to fix the violation. Okay, we know how to do the recolor and how to do the rotation, right? Okay, so what will we do? We will recolor and rotate nodes to fix the violation. One more point that I am to add to you. Before going into the details of insertion, let me show the relation of new node with other nodes and the different cases we may encounter. You know that it will violate the property 2 and 3, we know. But when we will insert one item, we may encounter different cases that we need to know. And we need to know the strategies to fix the violation. Not only the recolor, I should not say that way. How to follow the recolor and rotate, or how in which way we need to do the rotation, right or left, or which node. Okay, so that we need to know. For this we have different cases and different strategies. Let us look at that now. So first the Z's relationships, that means the new nodes relationships. You can look at here. This is the new node that you are inserting, and if this is the parent, it's simple, you know about this, and this is the grandparent. Now this is the term we may not know here, because the parent and this guy is at the same level and they have the same parent. My parents, or I can say the Z's parent, and this Y has the same parent. So Y is the uncle of Z. Okay, that is the point. So no, I will not talk much here. And now we can see what are the scenarios or cases we may encounter while inserting an item. First case, I am talking here the case and the solution, or you can see all the cases in one slide here. This one. You can see that. Let me mark. You can see that it may happen that the node that we are inserting, it is the first node and it is root. So color, and we know that we have decided to make it red color, so it is the red and it is the case on. Now I am not telling the solution strategies. I'll talk after this slide. So next on, maybe the uncle is red. Okay. You can look at here. This is the node that you are inserting and your uncle is here, so it is red. Or you are the right child and your uncle is red. Okay, so here you are the left child, uncle is red. Here you are the mainly the right side and uncle is red. So for this I wrote here or, and this is the case 2. Now you can look at the case 3. Uncle is black. Okay, uncle is black, yes. You can see here also uncle is black. Here we have also two cases. Sorry, two different scenarios. Okay, you can toilet two cases, but for these two things or two scenarios we have the similar solutions. For this they are together. For this also we have similar solution strategies. Okay, so for this they are together. So you can see that they are triangle like this. This is a angle triangle. Okay, this one, this one, this. So one more case or one more scenario. So the uncle is black but the relation you see line, and here uncle is black. Okay, here your uncle is black. Okay, so these are the different cases or scenarios. Let us now look at the solution strategies. Okay. Case 1, and it is the root, and it is the if it is one node. Okay, you know that it is one node. So then we set the color of the root to black. That means recoloring. Only recoloring is fine because we have only one node here. Okay. So this is the way it works. So now we can see the case 2. You can see that the uncle is red. Okay, uncle is red. So in this case, okay, you are here, two different scenarios may happen with respect to this condition. So what we need to do in this case, recolor Z's parent, grandparent, and uncle. Okay, just recoloring is enough. So what I did, you can see, I made the W and X black, and the X, the parent, is red. Okay. Similarly, you can look at this one, or you can look at this one. Okay, so this is very simple. Okay. Now we can look at the case 3. So we have two different scenarios we know with respect to this condition. So you can see that, you can look at here. This is the initial state after the insertion, and this is the initial state for case, for another scenario. This. So let me look at the one first. So what it is saying? It is saying that rotate Z's parent. Z's parent. So parent is W. So here is also W. Oh, we can do the both together. We can both scenarios together. In opposite direction of Z. So in this case, Z is in the right. So we are doing the left rotation. Okay, we are doing the left rotation in case 1, or I can say here we know it is case 3, but two different conditions we may encounter. Okay. So now if you look at here in this one, in the 2, you can see that the Z is the left child. So opposite direction of Z, that means rotate right. Okay. Rotate right, W, that means rotate right, W parent. Rotate parent of Z. Okay, so this. So when we do this rotation, then we will get like this. I know you know how to do the rotation, right? Left and right. You know how to do the left and right rotation. So this. Now you see that this one is line. Red, two red, and this uncle Y is black. Okay, and this uncle Y is black. So we can go back. Okay, I don't need to go back, especially this is case 4. Okay, this is especially case 4. Okay, so in case 3, if we do the rotation, we will reach to case 4, right? So we cannot solve the issue or violation or fix the violation. So now we need to follow the strategy for case 4. So how to do that? I am showing for only one. Okay, for if you have the we are only doing the when we have I'm showing for only one. So if you can read here first, that you can read here rotate. Okay, grandparent of Z. So grandparent of Z means X in opposite direction of Z. That means since it is the right child, so the opposite direction of Z means rotate left. Okay, rotate left. So we are rotating X to left. So if we do the rotation, then we will get this. We will get this. Think little, pay little bit attention. So you can see that we will get this. After that, we know the rotation before that. We know that the next node becomes the parent, right? So here W is the next one. So you can see that W is becoming the parent of X. Okay, and we know the intermediate node, this one, it will become the child of X. That means that was parent before. Okay, and and the child like Y or the child like Z, there will be no maybe interfere with them. So they will directly connect with the node they had was before. So for this, you can see that we get this. Okay. So when we get this, when we so after, this is the output of the rotation. Okay. I can clean and I can. Okay. So what can I say? If you do this rotation, then this is the output. Okay. This is the output. And these two are the intermediate steps. These two are the intermediate steps. So now it is saying recolor the original parent and grandparent after rotation. So original parent and grandparent. So original parent and grandparent. Parent is W and grandparent is X. So you can so W is the parent and grandparent is X. So you are recoloring. Okay, recoloring. So now you fix the violation. You have fixed the violation. So in this way it works. Okay. So what we can see all the scenarios in one slide here. So if it is the only one node, so that means it is root, just recolor it to black. And case 2 is, or scenario 2 is that if the uncle is red, then just recolor is fine. Now scenario 3, if the uncle is black and the relation is triangle, then rotate your parent and follow the case 4. Okay, this way. So now, and directly if we have the uncle is black and the relation is line, then we can rotate to the grandparent and perform the recoloring. Then we can get the maybe a red black tree. That means it will preserve all the properties of red black tree. Okay, so no more today. I have taken long time of you. So in no more today again I am saying in the next lecture I'll talk about the insertion in a great details. In addition, I'll talk about deletion of nodes. Okay. Uh, moreover, that moreover I I know that we should attend the lectures, but textbooks are the best alternatives for learning or the references. Okay, so if you want to more details about this, you can look at the references in the next slide. These are the references, and in the next lecture I have already told you that this is the context, insertion in details and deletion. Okay, in the meantime, if you have any questions, then you can write down in the comment section and I will get back to you. Okay, thank you very much for your patience and sorry for my long lecture. So thank you and see you. Have a nice day. Take care.